The impact of climate change on society is one of the most serious challenges of this century. Observations have shown that the Earth's hydrologic cycle has intensified during the past century as the Earth's temperatures have increased. Such change in hydrology will affect nearly every aspect of human well being, from agricultural productivity and energy use to flood control, as well as municipal and industrial water supply. These are the opening lines from the abstract of a study conducted by Pradeep Adhikari, Jinhua Jiang, and Yang Hong. This study, entitled Will the Bagmati Basin's Future Hydrologic Change Be Linked with Global Climate Change Patterns, was published in the British Journal of Environment and Climate Change in 2015. The purpose of the study is to try and predict the future hydrologic changes to the Bagmati River Basin in Nepal.
The study uses three greenhouse gas emissions scenarios from the fourth assessment report prepared by the Intergovernmental Panel on Climate Change. The scenarios are the B1, A1B, and A2, which range from the very conservative B1 to the very high emissions A2. Using a collection of 16 global climate models, precipitation and temperatures for the basin is predicted for all three scenarios for the years 2020 through 2029, 2060 through 2069, and 2090 through 2099. Using the predicted figures and the Thornthwaite monthly water balance model, the study would attempt to predict changes to the Bagmati Valley Basin hydrology compared to the base years of 1990 through 1999. The Bagmati Basin is a large basin located in south-central Nepal. The Bagmati River is the main outlet for the basin. Its headwaters start in the hills surrounding the capital of Kathmandu and continue south through three distinct climate zones before crossing into India and emptying into the Ganges River. The basin is a largely rural area that depends on agriculture. The climate of the region is driven by the South Asian monsoon, which in turn creates wet and dry seasons. 90% of the yearly precipitation occurs during the monsoon season, which typically runs from June through September. The steep slopes surrounding the basin, combined with torrential rains and the predominantly loamy soils, create an environment prone to floods and landslides. The 16 global climate models were made available through the World Climate Research Programme's Coupled Model Intercomparison Project 3, or CMIP3 for short. Initial analysis found that their temperature and precipitation figures had been biased and spatially downscaled when compared to observed data from 24 in-situ rain gauges located within the basin and discharge measurements taken at a station located near Pandera Dovan. It was found that the global climate models underestimated precipitation by about 18%. This is largely because the CMIP3 data cannot capture precipitation over 400 millimeters per month, which happens for most of the wet season within the basin. The CMIP3 data for precipitation and temperature was then bias corrected to improve the validation indices for the study. This bias corrected data then can be used to make predictions for precipitation and temperature through the three projection periods. This data will also be used as input into the Thornthwaite monthly water balance model for the three periods. The Thornthwaite monthly water balance model was selected because it is a simple model that requires minimal data, including mean monthly temperature, total monthly precipitation, and the basin's latitude. A good selection for areas of the world that lack significant amounts of data. This model was calibrated by comparing simulated and observational data to create a bias percentage and a correlation coefficient. This model was also found to have inconsistencies in the wetter months, again most likely due to the inability to capture runoff data larger than 400 millimeters per month. The difference was found to be between 10 and 13%. Using the calibrated model and the bias-corrected data, predictions about the decadal and seasonal variability of the hydrologic cycle for the region can be made. Predictions are made for several hydrological components, including precipitation, temperature, potential evapotranspiration, actual evapotranspiration, and runoff. These predictions were made for all three emission scenarios during the three time periods. Temperature for the Basin region is predicted to steadily increase in all three emission scenarios until about 2030, at which point the B1 or lowest emission scenario will begin to slow compared to the A2 and A1B scenarios. By the end of the century, temperatures are expected to rise by 4.5 degrees centigrade in the A1 scenario, 3.5 degrees centigrade in the A1B scenario, and 2 degrees centigrade in the B1 scenario, compared to the 1990-1999 baseline data. During the 2020 through 2029 window, temperatures during the winter are expected to decrease, even though the yearly mean temperature will increase. This means colder winters and hotter summers. For both the 2060 to 2069 and the 2090 through 2099 windows, temperatures are expected to increase year-round with increased variation between the emission scenarios. The 2090 to 2099 window shows a significant variance between the A2, A1B, and B1 temperature increases. Precipitation is also predicted to increase through the end of the century for all the scenarios, with expected increases of 20%, 15%, and 7% for the A2, A1B, and B1 scenarios respectively. During the 2020 through 2029 window, most months are expected to be wetter, with the exception of May through August and November through December. This means the traditional wet season of May through August will be drier, and that the traditional dry season will be wetter. This trend continues into the 2060 through 2069 window, except the summer months will also see an increase in precipitation. November and December continue to be dry, but the other drier months will become wetter, and the wet months will also become wetter. In the 2090 through 2099 window, there is much more variability between the scenarios and months, except for September and October, which are significantly wetter for all scenarios. With the increase in precipitation and temperature, as expected, there is an increase in the other hydrological components within the basin. This chart shows the increased anomalies compared to the base period for each emission scenario with the selected time windows. In all three scenarios, potential evapotranspiration, actual evapotranspiration, and runoff have increased. Plotting the increases monthly, you can see that the increases in each of the hydrologic factors get larger with the larger emission scenarios, with a slight increase in B1, slightly larger in A1B, and the largest in A2. Why are these increases important? In July 1993, the Bagmati Basin experienced the largest rainfall on record in Nepal. One rain gauge was observed at 540 millimeters per day. This precipitation event triggered massive floods and landslides that led to over 1,120 deaths. Using the data predicted, Adhikari, Zhang, and Hong were able to extrapolate for each scenario and each time period the number of expected extreme precipitation events equal or greater to the 1993 record year. In just the next decade, the Bagmati Basin is expected to experience some of the wettest years on record, and by the middle and end of this century, can expect to have precipitation events on the scale of the disastrous 1993 event almost every year, carrying with them the increased likelihood of landslides in the mountainous areas of the basin and increased flooding in the lowlands.
Based on the findings of Adhikari, Zhang, and Hong, contingency plans to mitigate and respond to floods and landslides, as well as water resource management policy for the Bagmati Basin needs to be revised. I'm Daniel Mashesky, and thank you for watching.